Okay, let's dive in. That weirdly shaped juice bottle you grab from the fridge,
Mhm.
or maybe like that curved yogurt cup. Ever stop and think, how do they actually figure out exactly how much fits inside? I mean, when it's not just a simple box shape.
It's funny, isn't it? We see them every day and don't really give it a second thought. But what's really pretty fascinating is that calculating the volume for those, complex curved containers,
Right.
it actually uses concepts straight out of university level math.
Wait, really? Like calculus?
Yes, exactly.
Calculus for a yogurt cup.
Yeah.
Okay, now I'm definitely intrigued. So this deep dive, we're exploring that exact connection. How integration, which sounds kind of scary, maybe is actually the key tool designers are using to measure the volume of packaging that isn't just, square or cylindrical.
Precisely. The main challenge is, well, figuring out the volume when the shape's dimensions keep changing. Think about a bottle, right? The width or the radius, it changes as you go from the bottom up towards the neck. You can't just pull out a simple formula like length times width times height. It doesn't work.
Okay, so how do they even start? How do they describe these shapes with math? Do they just sort of sketch it and then try to measure somehow?
Oh, no, it's much more systematic than that. It usually starts by defining the container's profile using mathematical functions. Imagine, like, slicing the bottle right down the middle, vertically. You see a curve, right? Well, that curve can often be described pretty accurately sometimes by a function. Maybe something simple like y equals the square root of x, or maybe y equals x squared. Or sometimes combinations of functions for different parts of the bottle.
Right, okay, so they map out the side view, the profile, using an equation. But that's just a flat line on a graph, a 2D thing. How does it become a 3D bottle or a cup?
Yeah. Well, this is where a really clever geometric idea comes into play. It's called a solid of revolution. What designers do is they take that 2D curve, that function y equals fx, defining the profile, and they basically spin it conceptually around an axis, usually the x-axis or the y-axis. Think of it like spinning clay on a potter's wheel.
Oh, I see. So you take that line from the graph, rotate it 360 degrees around, say, the x-axis, and bam, it sweeps out the 3D shape of the container.
Yeah.
So if you rotate y equals square root of x around the x-axis, you could get something with a rounded bottom, like some juice bottles have.
Exactly.
Or spin part of y equals x squared around the y-axis, maybe, and you get that sort of flared shape you see on lots of cups.
Wow. So you're turning an abstract line into the blueprint for a physical shape.
You've got it. That
Yeah.
function, fx, it now tells you the radius of the 3D shape at any point x along that axis you spun it around. But, like you asked earlier, just defining the shape, that's only part of the job. How do you figure out the exact volume inside that mathematically created solid? That's obviously critical for manufacturing, for filling it correctly, making sure the label matches the amount inside.
Right. That seems like the tricky part. You get this complex, curvy shape made by spinning a function.
Yeah.
How do you measure the space inside it down to the last milliliter? And that is where integration does its real magic. Integration, fundamentally, it's a method for summing up an infinite number of incredibly tiny pieces to get a whole. For these volumes of revolution, we imagine slicing the 3D shape. Think of it as countless infinitesimally thin disks stacked perpendicular to the axis we rotated around.
Slices, like cutting a salami, but impossibly thin.
Exactly like that, but mathematically thin. So each tiny slice is basically a very, very flat cylinder. And we know the volume of a cylinder, right? It's the area of the circular base, that's pi times the radius squared times its thickness. Now, in our case, the radius of each tiny disk at any specific point x is just given by our function, fx. Remember, that was the height of our original 2D curve. And the thickness, that's an infinitely small change in x, which we call dx in calculus terms.
Okay. So the volume of one super thin disk is pi times fx squared dot times dx. Got it.
Perfect. Now, integration is the tool that lets us add up the volumes of all of those infinitely thin disks. We do that all the way along the length of the bottle, say from its bottom edge XA to its top edge XBB. That integral sign, the sort of stretched S, it basically means sum up all these tiny volumes, these FX, DX pieces across the whole range of X. And the result, it gives you the exact, precise total volume of the solid you made by rotating that curve y-axis.
Wow. Okay, let me see if I follow. They use the function for the radius at every single point. Square it times pi gets the area of that circular cross-section. And then integration is like adding up the volumes of an infinite stack of those circles along the whole length. That's That's actually how they get the precise volume.
That is exactly how it works. It's a direct application of calculating volumes of revolution using integral calculus. And it lets engineers and designers know with incredible accuracy exactly how much stuff a container will hold, long before they even make a physical prototype. It affects everything: how much material they need, shipping costs, even making sure they meet labeling regulations.
So next time you're, pouring juice from a bottle or scooping yogurt from a cup, just remember that its nice curve probably wasn't just some random shape. It was likely born from a math function, spun around in space, and its volume calculated precisely using integration. That's kind of cool. It's math literally shaping our everyday stuff.
It really is, yeah. It just goes to show how even, seemingly abstract math concepts have very real, very tangible uses all around us. And maybe think about this. Beyond just packaging, where else might designers be using these ideas? Functions, rotations, integration. Maybe for creating and measuring other complex 3D objects. Things like, I don't know, car parts or musical instruments, maybe even furniture. The possibilities are kind of endless once you start looking.